Hello everyone, my name is Serena Hong. Today I'm going to introduce the very first chapter in fluid mechanics, the introduction. To begin with, we start from asking a question. What is a fluid? What is the difference between a fluid and a solid? According to the definition here, a fluid is a substance that deforms continuously when acted on by a shear stress. So let's look at the shear stress. A shear stress is created whenever a tangential force acts on a surface. So let's look at the figure here below. The figure below here is about the surface that we talk about. So maybe you can imagine that this is a cube, right? This is a cube. And I think for most of you, you have learned in your high school that if we apply the force here, we will call it the normal force, right? This is the normal force because the direction of this force actually is orthogonal to the surface. And then we just assume that this for this cubit here, the 6 surfaces actually have the same surface area, and we denote it by A here, right? So here you can see that there is a sigma t, sigma sub t, sigma sub n here. The sigma actually denotes the stress. So the sigma is the stress. The stress actually is defined as a force per unit area. So it is very intuitive that you can imagine sigma n here actually is the normal stress, which means that it will equal to the force in the normal direction divided the area per unit area. So similar with the normal stress. A shear stress means that the force comes from this direction, the tangential direction, and we will call it the shearing force here. Stress comes from this direction, divided by area, then we will get the shearing stress. So the shearing stress actually is denoted as the sigma sub t will equal to the tangential force. T stands for the tangential per unit area. This is the shearing stress. Shearing stress equal to the shearing force divided by the area here. So most of the time, you actually we will say that the shearing stress is more. We will draw like this. This is the shearing stress, the direction of the shearing stress, or this is also the direction of the shearing stress. It's just like the force acting the force acted on the surface. But the stress actually is equal to the force per unit area. It's defined as the force per unit area. So let's go back to our definition here. Definition said that a fluid is a substance that deforms continuously when acted on by a shear stress of any magnitude. So this part, deforms continuously, actually is the most important part, and is the most different part between the fluid and a solid. So maybe let me give you another example. You can just imagine a solid substance like copper. So this is a copper. This is also a qubit, okay? And then I just I just stick a copper qubit on the floor, and then apply a force, like what we just introduced. I apply a tangential force here in this direction. Then what will happen? This is the copper. This is the copper. And then if I act a force here, then you can expect that at next time step it might look like this. This is more dramatic part, but we just think about like this, right? It will deform. It will deform a little bit because you act a force like this. So the copper, the metal actually will deform. And then this kind of the deformation actually will stop. So what do I mean that it will stop? You just imagine that if today this is like this is the floor and this is the water. This is the water, and same you act a tangential force here. Then what will happen? The water certainly will not become like this, right? It will not become like this. It probably just look almost the same. You might just look like this, the same. Because the fluid particle actually will deform. They will run, but they will deform continuously. So it will not, the deformation will not stop. Unlike the solid substance, when you act a force on a metal, actually initially it will deforms and then you will stop immediately. The deformation actually most of the time are very small, and this is what you will learn in the maybe the material mechanics. You will learn about this part. And however, in fluid mechanics, we just told you that the fluid actually will deform continuously, so you will not see this kind of situation happen. Okay, so this is the most important part, is that a fluid, not particle, a fluid actually will deform continuously when they are experienced a shearing stress. So next part is telling about different types of fluid. The fluid including the liquids and the gases. The liquid like water, the oil, anything that you can imagine about. The gases like the air, the methane, ch1 in Chinese, methane. Next is about a very important concept when we try to analyze the fluids. It is called the continuum concept. For example, in this cube, if today it is full of water, then you can imagine that in this cube there are numerous fluid molecules in it. And because of the very large number of fluid molecules in this cube, it is impossible for us to study the behaviors of every individual molecules in this cube. Therefore, when we try to describe the behaviors of the fluids, or when we try to analyze the fluids, we will pick a representative point. Like in this cube, maybe it is the center of the cube. Then in space, the location will denoted by the XYZ here. So we will average the behaviors of all the surrounding fluid molecules in this cube. And then all the representative fluid characteristic like the velocity, the pressure, the temperature will be assigned to this point. The average is evaluated over a small volume, and this volume contains a large number of molecules. This is called the continuum concept. This is actually based on the assumption that we assume all the fluid characteristics like the pressure, the velocity, vary continuously throughout the fluid, which means that the value of the velocity will change continuously. And this concept actually can link back to the definition of a fluid. The definition said that a fluid is a substance that deforms continuously. This actually means that we believe that, or we assume that the force transferred in the fluid actually is transferred in a continuously way. So the definition actually will lead to this concept. Okay, so next part is about the dimensions. In fluid mechanics, we will deal with a variety of fluid characteristics. Therefore, it is necessary to develop a system for describing these characteristics both qualitatively and quantitatively. For the qualitative descriptions, this is the dimensions that you have already known. The qualitative aspect is to identify the nature, the fluid characteristics like the length, the time, the stress, the velocity, while the quantitative aspect provides a numerical measure of the characteristics. And this quantitative description requires both a number and a standard. The standard is the unit, which is also you have already known. The purpose of the unit is to compare the quantities. So the primary quantities, also called the basic dimensions, here we want to introduce you, is about the length. The length is L, the time T, the mass M, and temperature theta here. These primary quantities can then be used to provide a qualitative description of any secondary dimensions. And so the secondary dimensions is like the area, the pressure, the dimension of the area, the pressure, the velocity. So maybe we just look at the velocity here. The symbol here is used to indicate the dimensions of the secondary quantity in terms of the primary quantities. Therefore, this part, this is the velocity. This is the dimensions of a velocity equal to length divided by time. Okay? And the next example is about the sigma. The sigma is the stress. If you remember, we just have introduced the definition of a stress. The stress is equal to the force per unit area, right? Therefore, you can simply just find the dimensions here. The dimension of the stress is equal to the force, and the dimension of the area here is equal to the length square. Therefore, this is equal to force times the length minus 2, right? And this part we will introduce later. And in the engineering field, there are two systems of units. One is called the SI, the System International. The other is the BG unit, the British Gravitational Unit. These two are both very important, so you should know both of them. Okay. So to compare with these two units, this is the primary units in the SI system and the BG system. We list a table here. We'll talk a little bit more about the units here. Okay, so this is the SI. Oh, maybe I can write it here. This SI and the BG here. The SI, the mass in the SI, the mass in the SI system is kilogram. And the BG unit here is called a slug, the mass. And then it's the length. Length for the SI system is the meter, while in the BG system is foot. And the time is the same. Time in both systems are second. And the force in SI system is the Newtonian and a pound. For the temperature here, in SI system, the absolute, this is the absolute temperature, so the, oh my god, absolute temperature is the Kelvin, and the ranking, the degree of ranking is equal to the, let me check it. If you have the Fahrenheit, degree of Fahrenheit plus 459.67. Well, in the Kelvin part, you have to already know it's the degree of Celsius plus 273.15. Yep. So this is the unit in the SI unit and the BG unit system. The math, length, time, force, and temperature. Okay. So then we start. We give you an example. Is the pressure part? Pressure. What you have learned in the high school tell you that the pressure actually is equal to the force applied per the force, oh my god, the force per unit area, right? Pressure equal to the force per unit area. So the unit of the force in SI system is the Newtonian, and the area is equal to the length square, so it's the meter square. Then you can just find the units of the pressure, the Pascal, right? So this is in the BG system. You can just take a look at this part. Okay? Then next part is the dimensionally homogeneous equations. This is a very important property when we want to analyze the dimension, the homogeneous property. This means that the dimensions of the left side of the equation must be the same as those on the right side. So it means that if there is an equation here, if you got the equation here, the unit of A, what do I say? If it is equal to the meter square, then the BC, the unit of BC must equal to the meter square. This is called the dimensionally homogeneous. And just like it mentioned about all active terms have the same dimensions, it means B and C has the same dimensions. This is a very important property of the equation. Okay, so we give you an example. Is the flow through the orifice. This is actually a commonly used equation for determining the volume rate of the flow, and it works like this. You have a tank or something. This example, you have a tank, and then here is the orifice, and this part is the area of the orifice called A, and then first you have the water here. This is the water, and you get the height. the height of the liquid above the orifice. This is the orifice, and then you know that water will come out from this part. We want to calculate the discharge, and the equation work like this part. The discharge can calculate, the discharge can calculate based on this equation. Okay. So the A is the area of the orifice, and the H is the height of the liquid above the orifice here. And the Q here is the volume per time, volume of water per time. So you can see this part. And okay, so let's analyze the dimensions. Okay, so we know that this is the dimension of the Q is equal to the volume per time. So it's equal to the length cubit divided by time, right? Divided by time. And then this is the unit of the Q. This is the unit of Q. And the 0.61 is the constant. It is dimensionless, so it is not important. Put it here. The dimension of the area equal to the length square, so we put the length square here. And the square root has no dimension, so square root second 2. We just put it outside the square root, and then you will get here the G and H, right? G is the acceleration of gravity. So acceleration of gravity actually is equal, the unit of the dimension and unit of the acceleration is equal to acceleration of gravity is equal to acceleration, which is like what you learn in the high school. The unit of the acceleration is equal to, oh my god, equal to meter divided by the second, right? So the dimension of meter is length divided by time square. This is G. And because it is in the square root, so you should put it in the square root. So this is the G, the dimension of the G, and plus the dimension of the height is equal to L. Then you just put it in L. Then you can know that it just become like this in the dimension, in the square root. So because it is square root, you just take out of it, and then it is equal to this part. So put the constants all in front of the dimensions. Eventually, you'll find that in the left-hand side of the equation, the dimensions is equal to the right-hand side. This is called the dimensionally homogeneous equation. Okay? So now we are going to analyze certain property of the fluid characteristic, or I think it's just the basic parameters that you have to know. We will analyze the dimensions and the units. Okay, it is very simple. I think most of you actually have got some basic idea. So we will just do it very quickly, go through this part. So the first, like a Newtonian second law, force equal to the mass times the acceleration. Like we have just learned about, talk about the acceleration. The unit of the acceleration is equal to the unit of k is equal. The mass is equal to the kilogram, and then this is unit. Meter per square is the unit of the acceleration, right? And if you want to analyze the dimension, the dimension of the mass is equal to m, right? And this is meter, so the dimension of the meter is equal to L, and then divided the second is the time, right? Time t square. Therefore, it is equal to the NLT minus 2. Okay, this is a dimension analysis. And for the BG system here, this is the BG system. We will call it like what we just write about. This is the mass in the BG system, a slug, times the acceleration equal to the foot per second square. Okay, this is the unit in the BG system, and the units in the SI system, which we are more familiar with, is just work like this, and this is called a Newton. The abbreviation of the Newtonian. Okay, N, and then this is the pound in the BG system. For the weight, it's more like this. It's just similar with the force. The difference between the weight and the force is that it times the g here. Yeah, is that the weight is the force on Earth. Therefore, the acceleration is equal to the g. So actually, it's almost the same, I think. F equal to ma, and in the gravity here, we just the gravity acceleration, then is mg, which is equal to the weight. This is the definition. And then, so similar, it actually comes from the force, so it is the dimension is the same. And then because it is the acceleration of gravity, so you have got some kind of the constants behind in front of the unit, and this is the constant. Maybe you should know. You have already known. I don't know. Okay. Anyway, these two parts is the standard gravity on Earth. This is no doubt. And next part is the work. Work is the product of force and displacement. Like what you have learned in your high school, the work equal to abbreviation is W equal to the force times the displacement, right? Therefore, the force, what we have learned, the dimension of the force is equal to NLT minus 2, and then times displacement. This is the displacement, right? Displacement L. So the dimension of the work is equal to the mass times then square T minus 2. Okay, this is the joule. The joule is the SI is in the SI unit, equal to the force. So it is N times displacement length. Okay, so it's meter. And if it is in BG system, this is for the SI system, right? If it is for BG system, the definition, because it's the same, it is called percent work is foot times pound. And the pound is the unit of the force, and the foot is the displacement. Then this is called an erg. This is in BG system. Okay. And then next, the last one is power. Power is the rate of doing work. So actually, the power, the units of power W here is watt, right? And the dimension of the power, because the power is equal to the work per time here, so the work dimension of your work is this part and times per time. So the dimension of the power is mass, then square T minus 3. Okay? Then this is the unit. 1 watt is equal to 1 joule per second. Okay? This is the basic analysis of the unit and the dimension. Okay? Next part. Next part is about some basic fluid properties or the fluid characteristics. When we want to, just like when you want to introduce yourself to your friend or your new friend, you have some basic properties that you can tell them, that you are a girl or boy, your how tall are you, and what age is your age. Okay, so is this something similar? If we want to analyze the fluid's behavior, then we should tell some basic property of a fluid. So this part is very simple. We just quickly go through this part. The first is the density, because the definition of the density is equal to the mass of the unit volume. If we want to compare if this fluid is heavier than that fluid, then you could compare the density. And this is the unit of the density. There's a simple note. Maybe density here. He mentioned about the density of gases is strongly influenced by temperature and pressure. So if you want to analyze some kind of a fluid like the gases, you have to look on the table to find the temperature and the pressure. Then you will get a specific or a corresponding density of the gases at that kind of a situation. Second part is the specific volume. Specific volume is equal to 1 divided by the density, which is the volume of the unit mass. This is the definition of specific volume. This is just equal to volume per mass. Okay. And then the third part is the specific weight. A specific weight is equal, we call it the gamma, is equal to the density times the acceleration of the gravity. This is the weight of the unit volume, which is the weight per volume. And this is the unit here. Okay, this is very simple. And another one is a specific gravity. This is the ratio of density of a fluid and the reference fluid at the reference temperature. Why we want to choose this like the density at water at 4 degrees Celsius is just because that we have already know that the density of the water is the heaviest when the temperature is equal to the 4 degrees Celsius, right? If you remember this part, I think it's maybe in your junior high school. I don't know. So this is your density in water density. Is the unit is the kilogram per meter cubic, and this is the temperature. So if this part is 4 degree, then you will know that it's worked like this, right? And this the biggest part at 4 degree is equal to 1,000 kilogram per volume, right? And if you want to know, I'll write it here. Okay, this is the water density at 4 degrees Celsius is equal to the 1,000 kilogram And then if in the BG system, this is equal to the 1.94 slug. Remember, BG system, the mass is slug, and foot cubit. Okay, this is the specific gravity. Then next part is the ideal gas law. Ideal gas law. Okay, ideal gas law, also called the perfect gas law. I think you have already learned in your high school. Also, this is equal to the equation is the density, the pressure equal to the density times the gas constant and absolute temperature. This is the T here is the absolute temperature. Okay, this is, you must be very careful about this. And an absolute pressure here he talk about absolute pressure equal to the standard atmospheric pressure plus the gauge pressure, and this standard atmospheric pressure here is equal to 101.3 kilopascal, or if you in BG system is the 14.696 psi. Okay, so next is the what we have introduced before is about the absolute temperature. If you are in the BG system, then it's 1 degree Rankine, right? Degree of Rankine is absolute temperature. Is this equal to the degree of Fahrenheit plus the 459.67, and if it's in the SI system, then it's the Kelvin. Degree of K, no, it's only K, is equal to the degree of Celsius plus 273.15, right? So our following is the example. So if we want to calculate the absolute pressure here, the P is the absolute pressure. I will just link them before absolute pressure. Then you just put all the condition in it. We got the volume is equal to 0.84 foot square. Gauge pressure is equal to the 15 psi. So this example is in the BG system, the BG unit, okay? BG unit. And then the gauge pressure is equal to 50 psi, and atmospheric pressure is equal to the standard atmospheric pressure. Temperature here now is the 70 degree of Fahrenheit. So this is your equation, right? You got the density equal to the absolute pressure divided by the gas constant and the absolute temperature. Put all what you have known in this equation, then you will get the density. Okay, the density of the, it didn't mention about, maybe it is the density of the gas. Okay, this is that if this is the density of the gas, then you could calculate the weight of this yeah, you only mentioned about volume, this volume, how many weight of this substance in this volume, and it's the 0.276 pound. Okay, next is the viscosity. Viscosity is very important. Probably this is the first time you heard about this, so we will spend more time on this part. Now let's talk about the viscosity. Viscosity in Chinese is called 粘滞性. It is the resistance of a fluid to flow. So like the very simple definition here, the viscosity of a fluid is a measure of its resistance to flow, which means that different fluid with different viscosities will flow at a different speed when the same force is applied to them. In a more daily example, You can imagine that today you want to pour out some honey into your cup. Then you will find that use the same kind of gesture and the same amount of water in the honey, the flow of the honey is much more slower than the water. It is because the viscosity of water is very small compared to the honey. Therefore, for the fluid particles, they are not resist to move. And this will lead to another concept about the viscosity, is that it is somehow it can represent the force required to induce the flow movement. And next, in order to determine this property, we can consider experiment here. So in this experiment, there are two plates. The lower plate here is fixed on the floor, and this is fixed, or you can call it stationary. Stationary on floor, and the upper plate. Okay, upper plate is a moving plate. I will write it here. This is the moving plate. This is the fixed plate. Okay, and why we say that it is a moving plate? It is because that we apply the force in this direction. So like what we have learned before, this force actually is the shearing force. Okay, we apply the force here, and eventually the system becomes steady and the plate will move with a constant velocity u here. Okay, and about other information is that the gap between these two plates, wow, the plates between these two plates is b, which is consistent with the lecture notes. Okay, it's b. And let me check a little bit. Okay. Okay. And the direction, the coordinate here, this direction is y direction, and this part is the x direction. Okay. So in this situation, we can assume that after the system become much more stable, then the upper fluid particles which contact with the plate actually will move with the plate with the same velocity. And the same condition happened at the lower plate. Fluid particle here actually move with the plate, which means that the fluid particle stop here. Okay, this is called the non-slip condition. I write it here. This is a non-slip condition, or you can say that it is a non-slip boundary conditions. Boundary conditions. Okay, non-slip boundary conditions. Okay, so we called the fluid velocity here small u. Okay, so for the non-slip boundary condition, it means that the fluid is moving at the same velocity with the boundary. In this case, the boundary is the plate, so it moves with the plate. So for the fluid particles at the upper plate, it moves with the velocity u, and the lower plate, the fluid particle just stop here, stationary, right? So for these non-slip conditions, when y equal to 0, velocity equal to 0, when y equal to b, which is the gap between the plates, the velocity equal to the bigger u, right? This is for our non-slip conditions. And then another assumption is that today we assume that the gap between these two plates is actually very small, which means that we can simply assume that the the velocity is linear. Okay? If it is linear, then you can write the velocity equation very easy. It will become very easy. Okay? So U will become what? The U will simply become a larger U, and right? Your velocity, your full velocity actually vary with height, and this is the very basic information we can get from this figure. And then now we assume today there is a small time increment. Means that in the next time step, the time step is very small. So if you can imagine that this is one free particles, and corresponds to this particle, this is another particle, right? And after a small time increment, it will move to here. This is a very small time increment. We call it delta t. This is very small, okay? And then for the lower fully particles at the lower plate, and it just not move, right? So for the next time step, it just stop here. Then this is what we call the deformation, okay? This is a deformation, and you will know the displacement, right? Because you know that this is its velocity is u, and then it experiences a small time increment, means the displacement is equal to u times delta t, and then this we give it a parameter. We call it delta alpha, okay? And then this deformation, we can simply think about, we give it another, we call it the delta beta, yeah, which is the same. It's the same in your lecture note, okay? This is the deformation, we call it delta beta. So if today the delta t is very small, then the delta b must be very small. So you can imagine that it will not look like this. Actually, it might look like this. I can use it might look like this, okay? A very small time, then you will come, and you cannot even see the displacement. And I just draw it more dramatically to let you understand. So in this case, if the delta t is very small, then the delta beta is equal to the tangent delta beta, right? And it will equal to tangent part delta alpha. And then we know that delta alpha is equal to u times the time increment. So we get the relationship between the beta here, beta, beta and the time. Beta in the time and the velocity and the gap, right? Now, what we are interested in is actually not the beta. We want to know the changing rate of beta. What do we mean by changing rate? Changing rate means that we want to know, along with time, how is beta changing. So it is very intuitive that you can get this formula, right? And this is called, we can call it gamma dot. This is the rate of the shearing strain. But the delta beta actually is a shearing strain. It is a strain caused by a shear force. Okay? We want to know the gamma here is the delta beta divided by the delta t. And in this situation, we give it another condition or restriction is that we want the delta t very, very small. Okay. Then you can just substitute this relationship into the gamma here. So you can get this is will equal to here delta beta is e u increment divided by db, and then right, and then there's no delta t, so it will become the u divided by b, right? This is the rate of the shearing strength. Maybe I highlight it a little bit. This is the rate of the shearing strength. So we now know the rate of the shearing strength. And then in fluid mechanics, all you have to remember, actually, everything is about the shear stress. The shear stress is very, very important. And now here, the shear stress denoted by tau. Tau here, shear stress. And shear stress, we will know that it is the basic information we certainly know. The shear stress actually is proportional to the shearing strength. The shearing strength is beta, and also proportional to the rate of the shearing strength, right? So the relationship between this part is certain. And then including in order to that the proportion to become equal, then we should add a constant, right? So this is the viscosity, the constant. Viscosity is called mu. 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 Okay, this viscosity is called mu. Mu times the rate of the shearing strength. So this is in this situation, this is the u divided by b. And this equation we divided based on the linearly change of the flow velocity. So if today the change of the flow velocity is not linear, then we should write it as this part. We want to know the change in velocity along with the y-axis, right? So this is the relationship, the main relationship between the shearing stress, viscosity, flow velocity, and your position. Okay, this result indicates that for a common fluid, the shearing stress, this tau here, and the rate of shearing strength and velocity gradient can be related with the related in this form with the viscosity. Okay. And the list viscosity, we also call it the dynamic viscosity, or simply the viscosity, or absolute viscosity. We'll look at the lecture note later. This is it has a lot of different names because later part in your journey to fluid mechanics, quite often the viscosity will appear with the density in this form. And this maybe I use another color, use the purple one. Okay, this is called the nu. This is a nu. Nu is equal to the absolute viscosity divided by the density. And this ratio is called kinematic viscosity. Okay, so let's get back to the lecture notes. We have just introduced about the viscosity. Therefore, now we just quickly go through the lecture notes, okay? So, viscosity actually related to the velocity profile. And in this velocity profile, this profile actually is linear. linear profile, right? It's a linear profile. And if you acted here is the figure, the demonstration of how we derive the viscosity, the relationship between the shear stress and the viscosity. So we just quickly take a look at this part. And there are two plates, and at the boundary plate, this is a fixed plate, while at the upper plate actually is a moving plate with the velocity equal to u, and then the gap between two plates is equal to b, right? So the velocity profile here is assumed to be linear, and then if a particle start from here, and at very after a very small time increment it transported to this part, we will know that displacement is equal to the delta alpha, while um, the angular deformation is delta beta, right? So because the time increment is very small, therefore we have the mathematical relation about the tangent delta alpha equal to delta beta equal to delta tangent delta beta equal to delta beta, and equal to the basic definition of the tangent. And then so we will get this relationship. So next part is that eventually we actually want to know the rate of the shearing strain, right? Because the force acting on the upper plate is the shearing force. Therefore, the strain is the shearing strain. So we want to note the rate of the shearing strain, which is the rate of the angular deformation. So we just want to know that the rate. Therefore, we just put the delta beta divided by the delta t, and then because we want the time increment to be very small, so we put a limit here. Then if the velocity profile is linear, we could get this relationship. If it is not, then it simply looks like this, right? We want to note what is the velocity change along with the y-axis. And yep. So then we would know that the shear stress actually is proportional to the shearing stress. I'm sorry. The shearing stress actually proportional to the shearing strain, and therefore you can get this relationship. Okay. So another information is that if the shearing strain, the rate of the shearing stress is linear, then we will call it a Newtonian fluid. And if it is not linear, then it is not a Newtonian fluid. So this part, next part here, discussed about the dimension of the viscosity. So it is simply because viscosity is here, so you can derive the dimension according to this relation. So we know that shear stress actually the dimension of the stress equal to, again, stress equal to the force divided by the area, and therefore this is your left hand side of the equation, and then you got the viscosity, so you don't know the viscosity, and then you got the velocity and the length, because the y direction actually represents the length, right? So you will work more like this. If you want to know the dimension of the viscosity, then you just should write like this. This is equal to the shear stress dy du, right? So the dimension of this part is equal to the force divided by length scale, and the y here is the length. The velocity here is the length per unit time. So like this, Ft L square. Yep. So it is, yeah. So like this part, this is the dimensional. This is the dimension of the Shearing stress. This is his dimension, and then this is the wow, oh my god, this is the dimension of the viscosity, which is we derive here, and then this is the dimension of the du dy here. And this kind of the viscosity here, we will call it, sorry, we will call it the dynamic viscosity, or simply viscosity, or we will call it the absolute viscosity. It is because that most of the time in fluid mechanics, the viscosity often appear with the density, and therefore we will use another kind of viscosity. We call it the kinematic viscosity. Here, the kinematic viscosity is called mu. Mu is equal to the absolute viscosity divided by the density here. And here talking about the Reynolds number. This number actually is very important, and I think we will introduce it later, but you have to know that why is viscosity so important, because viscosity is can reveal certain property of a fluid, and this is the very different part between the solid substance and the fluid, because in the solid substance there is not much theme about the viscosity, right? So when we want to analyze a fluid flow, we want to analyze the flow. Actually, there are different kind of the parameters or the numbers that we will introduce later, and most of the time they were related to the viscosity, because like what we said before, the viscosity actually reveal the resistance of a fluid to move. Yep. So like the Reynolds number is this a very important number in fluid mechanics. The Reynolds number Re here stands for the first two parts, the Re here, and it is equal to the density, and here is the characteristic velocity, and the characteristic length divided by the viscosity. So if like what we just mentioned about, if you can imagine that this is some people, or sometimes we will write like this, right? Then this time the absolute viscosity will become the kinematic viscosity. So maybe next time when you look, when you see the Reynolds number, you will just look like this. This is the nu and the velocity and the characteristic length. Or sometimes we will just write, oh my god, mu, v, and l, because this is the characteristic. What do I mean by the characteristic? Characteristic length, and this is the characteristic velocity, right? It means that in different fluids, it has different velocity, and of course there are certain kind of different length. This is just like if this is a pipe flow, the flow flew in a pipe, then what is the characteristic length? It is the diameter of the pipe, something like that, okay? And this part is denotes the property of the fluid, the viscosity, the kinematic viscosity, okay? So you have to remember that, because if you mention about the kinematic viscosity, the dimension is different from the absolute viscosity. Now we are talking about an example of the viscosity, and in this example, it is different from the situation that we have faced before. In this time, the two plates all are fixed, and therefore, based on the non-slip condition, you will find that the velocity profile at the two plates, the boundary part, is equal to 0. This is the non-slip condition. So in this situation, you should put your center point at the center. Yep, so your y equal to 0 is start from the center. Therefore, you will know that your non-slip condition will become like u h equal to 0, u minus h equal to 0. This is your non-slip condition. It's very simple. And in this case, the he will give you the velocity profile like this part. The this is known. This is the given condition. Okay, and because we know that the shearing stress is equal to viscosity times the velocity profile, then not velocity profile, it's the du dy. So it's a very simple example. You just put all the information here. So you divided the velocity by y and then do the simple math, you will get the answer. So the answer you'll get like this, right? So if I ask you about what is the viscosity at the boundary, then you can just simply put the y when y equal to h or y equal to minus h, you will get the boundary shearing stress, right? This is the boundary shearing stress. Now we are talking about the compressibility of fluid. The first, we want to talk about the bulk modulus. You can characterize compressibility of a fluid. So the situation works like this. Originally, you have a fluid here. This is your fluid. And then it got the original volume. Above the fluid, there is a pressure. And then something happened. Means that maybe there are more force, you act the force like on the container or the air, like the air on it. So the pressure become heavier. We say this P plus the change of the pressure, okay? So originally the volume of the fluid is in this line, and then maybe it become very heavier. So the volume becomes smoother. But then it's the original volume plus the change of the volume, right? So the bulk modulus actually care about how many pressure difference you have to add it to create such kind of the differences of your volume. So this is the definition. Let's use the color. This is a definition here. Okay. How many pressure difference you have to add it on the original volume to get a certain change of your volume. And then because we know that the mass is equal to the density times the volume, and on Earth, because the gravity will not change, therefore the mass is nothing to do with the gravity. Anyway, because the conservative law, so the change of the mass is equal to 0, and then therefore you can simply write the conservative law. So the mass is the same, right? The original mass is equal to the later mass. And how do we calculate how do we calculate the mass? Is equal to the density times the volume. Therefore, so for the original part, the mass is equal to original density times the original volume. And after the situation happened, the density will change, right? Because the volume change. Okay, so the density change, we just call it the original density plus the difference between the density. Okay, so this is the word like this: low plus the change of the density times the volume plus the change of the volume. And actually, this kind of change might be very small. So you just do some math, okay? So you can find that some parts will disappear, okay? So low TV plus V low plus low TV, okay? This part disappear, and then we assume that the change are very small. The volume change will become very slow in fluid, so this part is neglected, and therefore you will get the relationship work like this, right? So this is this part. Oh, okay, is here, okay. And then because you have this relationship, you just bring back to the original definition, right? You put the density, all the density on the left hand side, and the volume at the right hand side. Then bring back, substitute back to your definition. Finally, you will get this relationship. This is the bulk modulus. So we will use it later when we introduce other property of the compressibility, and then we will use this relationship. Okay. So the next part is about the compression and expansion of gases. Now we focus more on the gases, okay? Because according to the box modulus, you will never see that because the fluid actually like the liquid, like the like honey, if you give some kind of the force on it, actually the volume seldom change. Therefore, most of the time we will say that the fluid is incompressible. So what kind of fluid is more sensitive to the pressure change is the gases, right? Therefore, when we talk about the compression or the expansion, often is related to the gases. And now for the gases, for the compression and expansion, there are two situations you have to um, aware. The first one is isothermal isothermal process. This process means the temperature is constant. Temperature is constant will lead to this relationship, like the pressure divided by the density is a constant. And the second different situation is the isentropic process, which means that no heat exchange in this kind of the circumstances. Therefore, the relationship will become like this: the pressure divided by the density, and there is a K here. K is the ratio of the specific heat at constant pressure, okay? This is the specific heat at constant pressure. And sometimes you will see that the constant pressure like C sub P to the specific heat at constant volume. Okay, Sometimes you will see is this V, volume V, and then there are some relationship between these two constant pressure and volume. The K actually equal to the ratio of Cp and Cv, C sub V. And how to get these two constant? It depends on the gas constant, which you have already learned in your ideal gas law. Is equal to C sub P minus C sub V. But it is not very important. Most of the time, when you want to find the K, you just to check the table and to find a certain pressure, certain temperature, then you will get your K. Okay. So following is the example. So he mentioned about a cubic foot of helium. So for the helium at 14.7 psi is compressed isentropically. So he mentioned about isentropically here, isentropic process. So you get the relationship, this part. The pressure, remember the pressure is the absolute pressure, okay? The pressure divided by the density with a certain kind of the ratio, certain kind of the constant K here, and this will equal to a constant. Therefore, you mentioned about it compressed the air, the helium is compressed isentropically to the half of the volume. Then what is the final pressure, right? So because this is isentropic process, it means that this ratio is a constant. Then you just write the I here stand for the initial, okay? I is the initial, I is the initial, and the F stand for the final, okay? In this example, F stand for the final. So if you want to find the final pressure here, you just do some math and then you can get this relation and then put back all the information you know. In this case, it doesn't mention about what is the value of K, right? So you have to find the K. And the K is for helium, so it is 1.66. This is for helium. For helium. If it is for air, K for air, most of the time we will assume that the K equal to 1.4. Okay. Okay. Next part is about the speed of sound. Speed of sound is just like what you remember is that sound, the speed of the sound. Okay. So this is the definition. The speed of sound is related to the change in pressure and density of a fluid medium. So when we talk about a fluid medium, in this time you can imagine that maybe it is air or something. So it works like when there is an airplane flying through, and the airplane, when the emotion, they will compress the air, then the sound speed will change. The speed of the sound will change, right? So this kind of situation is what we are talking about. And so the definition here, this is the speed of the sound. The C is equal to the differential change in pressure and differential change in density. It's a small change in the pressure and density. And according to what we have learned in the bulk modulus, what this part, bulk modulus is equal to here the change of the pressure and change of the density, the original one, this one. So the definition like this, we can just substitute the relation in it and get the speed of the sound is equal to another form like this. And then for isentropic process, if you don't remember, the isentropic means that certain ratio is a constant. The certain ratio is I want to find it. Okay, here is equal to the pressure, absolute pressure divided by the density, and there is a constant K here. Okay. So now here, following is the deviation, the derivation of the. He just want to show you that the sound of the speed finally will equal to the square root of the K times R, which is the constant of gas and the absolute temperature. So now we just quickly take a look at this part. Because that we know it is isentropic situation is an isentropic process. Therefore, it is a constant when the absolute pressure divided by the density of the K, alright? So we know that the pressure will equal to constant times this part, and then to take the derivative. So you will know that the dp here, the constant is still the constant, will equal to put down the indicator here, the K, then it will become the dou K minus 1, and now we will get our derivative density. And then because we have our relationship here, the bulk modulus here, so we can know that the bulk modulus will equal to the dp times divided by the low divided by low, right? So put this back, and then we could just do some math. Then you will find that eventually it will look like this. So when you get this relation, you just go back to the isentropic relation, and you will find that the constants times the low k here is equal to p, right? P is equal to the constant times the low k here, and then therefore your bulk modulus will become p times k, right? So if it is become p times k, then back to our definition of the speed of the sound. The c is equal to the modulus, bulk modulus divided by the density. So bring back, substitute this bulk modulus, you will get the low k. C is equal to, yep, I'm sorry, this is a P, this is a P, okay, P, okay. And then this is the absolute pressure, so it will become, finally it will become like this. Anyway, it's just, it works like the ideal gas formula. Anyway, okay, so this is a derivative of the speed of sound, and if you want to do some, practice or exercise, this is some kind of example. This example is about a jet aircraft flies at the speed of this speed and altitude at this height, the foot. The temperature is minus 66 degrees of Fahrenheit. Remember, it's Fahrenheit. And assume that like this. This is the question you will give you. The K is equal to 1.4 is for air, and then he want you to find out what is the speed of the sound. Then because we have this relationship, So you just bring all the information in this equation, then you will get the answer. But you have to remember that the temperature here actually is the absolute temperature. And according to this question, all the units is in BG units, right? The British gravitational unit. So you must be careful about the units. Then finally, you will get the speed of the sound is equal to this part. And this is the Mach. Mach equal to velocity divided by the speed of sound, right? So you just put all the information in this again. You will get the Mach is equal to the 0.829. Finally, we are at our last part about the surface tension. I think most of you in your high school have learned a lot about this part, so it will be much more easier. Okay, so now we know that it is a tube, and there's might be a water or something. There is a tube here, and the tube with a diameter equal to the radius is equal to r. Okay, and then we take a look at the different the surface tension. The surface tension actually is equal to the intensity of the molecular attraction per unit length. Okay, this is the definition, and in this textbook, the surface tension is denoted by the sigma. This is the surface tension. So back to our example, you know that this is a tube, right? So the water weight or the fluid weight of in this tube is equal to the volume times the density. Yeah, specific density here. So the volume of this tube is equal to the area equal to pi r squared. So the volume is the pi r squared times h times the specific density. This is the fluid weight here. Yeah. And then there is our surface tension here. And the surface tension is happening at the location of surface tension happened at the surface here, along with the perimeter. Okay. Therefore, we will times the perimeter of the tube, which is equal to the 2 times pi and r. Okay, this is the perimeter of the tube, and then times the surface tension, and because the force balance must have at the same location, so we times the cosine alpha here. We assume the angle here is alpha. Then these two are the same, and therefore we will get our surface tension here, right? So it works like 2 pi r squared h comma divided by 2 pi r and cosine alpha. And if you do some math, then you will get this is the half r h comma times cosine alpha. Okay, very simple, very easy. So this is the final part of the chapter 1, all about the introduction. This introductory chapter, we discussed several fundamental aspects of fluid mechanics. We start from the definition of a fluid, and then it's the continuum concept when we try to analyze a fluid. Also, we introduce the dimensions, including 2 different systems, the SI system and the BG system. in the unit system. And of course, we introduced the various important fluid properties, which includes the fluid density, specific weight, specific gravity, and maybe your first time, the viscosity. Also about the compressibility of a fluid, including the bulk modulus, the speed of salt, and finally, it's the surface tension. Yay!